Okay, the previous chapter we understood how this formula of m by I is equal to sigma b by y is equal to E by R can be used to find out the stresses in the bending stresses in beams, and we also, if this bending stress in the beam is limited due to its material, like if it's steel it could be maximum like 400 to 500, if it is wood like it could be like 30, then we can find what is M for that beam. Then for that we can actually decide what should be the section of the material. So I is BDQ by 12, y is equal to d by 2. So like this, if these two are known for a beam, the bending moment applied on the beam, the material of the beam which decides the maximum bending stress, and this M are known, then we can decide on the geometry of the beam. This was the use of this bending equation that we taught in the earlier chapter. Now we are moving into a new chapter where we find a similar equation. Okay, that's in this chapter. What we saw was a beam which was straight, applied with a moment like this, applied with a moment M. That means this whole beam is subject to a bending moment M, and this actually starts bending like this. For this beam, it actually makes a radius of curvature R, and this beam has got a Young's modulus E, and this sigma is the stress at any fiber which is at a distance y. You can take this y as 0, you can take this y as equal to d by 2 or whatever, and then I gives, now if you look at this end from the other side, you can see what is the section. Now the section can be a rectangular section, it could be a circular section, it could be a triangular section, or it could be an I section or whatever. It could be an I section or whatever. Depending upon that, you can actually find out I, and therefore using all these combinations you can find out what is the size or the dimensions of the beam which is required. So basically for engineers, we come across a lot of components which will have bending forces. So if suppose those components should not fail, you should be aware of this equation. Of course, people say you got softwares like ANSYS which do the analysis for you. But basically to start with the analysis, you should have some dimension. So you should have made some hand calculations approximating a lot of things. So only then you can start with some dimensions, because ANSYS doesn't give you the dimension of the component. You should make a component and then you should feed it to analysis softwares with the loads. Then it will give you what is the maximum stress in the whole of the beam, or it will give you what are the stresses actually spread across the beam. So you are required to decide whether it is safe or not. Okay. So therefore, software doesn't give you the dimensions. So initially to start with something, you need to actually do this. Even in the case of a simple, you can say, can anybody guess what is this? I'm trying to draw. I'm not sure whether my drawing will help you guess this, but I'm only trying to say if somebody can actually understand what is this. Anybody can say what is this? Brake lever or a clutch lever. A brake lever or a clutch lever. So of course you can actually have a hinge here. This actually joins with a cable. Okay. So when you are applying the load here, so basically this is like a cantilever. Basically this is like a cantilever, and this section, is it circular or elliptical or what this is? This section, basically along this, is it actually square? Of course, a square doesn't aesthetically appeal to us. Okay, it's not even circular exactly, because circular means it will actually pain your, and I think it will actually cause some pain on the fingers. I think in new Royal Enfields they have almost made it elliptical, where there is a large amount of contact on your fingers so that it doesn't pain. It is almost like flat on the one side. Okay, so something like this. So even to design a brake lever, you need this equations. You need what is the force. If you know what is the force, then you can consider this is a cantilever. Then you can say that the maximum bending moment is here, which is actually P into L. Max is P into L here. Then you can substitute this here. Then you know what is the section. Then you can use this here. Then if you know the material, whether it's aluminium or any powder metallurgy metal, what is the maximum stress it can take, then you can substitute this. Then you can decide what should be the minimum section to actually safely hold it. Of course, nobody would actually break it by applying a force. Usually it breaks when a bike falls. Okay, it's simple example, but I think it would be a very wrong design if somebody applies a huge amount of brake force with his fingers and it breaks. That doesn't happen easily, but I'm only giving an example. So it happens with every component in a vehicle, whether it's a swing arm or any other component in a vehicle which is under bending. So it could be the chassis of a vehicle. Now you saw this equation, no? So it has 6 terms in it. Similar to that, you have similar equations in the torsion. Similar equation in torsion. So first of all, I'll actually explain you what is actually torsion. So torsion is basically twisting moment. Okay, just explain you what is bending and what are the components in automobile which would actually experience bending moment. Okay, I feel so. Can you have some components in mind before that? Before I tell you, can you say what are the components under bending in any vehicle? Maybe let's take a bike. What are the components under bending? Okay, give an example of a lever, brake lever or a clutch lever. So apart from that, handle. Exactly. Handle is again a cantilever. So of course fixed at the center. So overhanging on both sides, it's like a cantilever. At least if you see the one side. And then
Brakes.
Brakes means what? What brakes? Which pan? Which? Is it foot lever? Foot lever is also. So brake levers, foot levers, all. So all the levers. Whenever you say a lever, it is almost like a cantilever. And maybe it is the reason why there is cantilever. That term lever is there. Maybe. Okay. And then so now what would be the type of load in this rear wheel? Rear wheel, and it's held on this. Now what is this component called as? Swing arm. So swing arm, you will have a spring here. Okay, you will have a spring attached here. Okay, so it is hinged here. It is hinged here, and this is trying to apply a load from the wheels like this, and there is a load coming from the top because of the weight of the vehicle. It's again like a beam, and it's under bending. When you want to design a swing arm, you should be able to initially start with some values of the sections. Whether the swing arm is right now, I think we would have observed different types of swing arms. Whether the swing arms are circular, are they circular? They are rectangular in the newer bikes, but they were actually circular in older bikes, like Hero Honda and all. It was easy for anybody to make a circular rods. So it was usually circular. Nowadays it is coming as rectangular sections. Okay, so you can definitely know that. So when you know that, then you can actually use these values of the maximum bending in this, the material sigma B here, then you can find I by Y here. So that will actually decide the dimension. And once you have done that, then you can actually model this and actually put it to ANSYS and then analyze components. Of course, people don't need to analyze this with ANSYS because I think it's definitely easily predictable. But if it's a complex component with a lot of loads on it, then you need ANSYS. Okay, now I'm trying to compare this equation of bending to equation of torsion. Okay, in the case of torsion, you will see a rod. Basically, I imagine a component which looks like this. When you want to twist something, suppose if I want to twist this pen, can I hold it from one side and start twisting with one hand? No, you need to hold it on the other side, fix it, and only then I can twist it. So basically this end has to be fixed. Only then I can apply a torque here. So that's called as an anti-torque. Okay. So it will try to resist the twisting, and therefore you start actually twisting here. When you start twisting here, if you call this point as B, if you call this point as B dash, if you call this point as B, if you call this point as B dash, now after applying a torque T, this starts, now suppose if you add, I think I saw a video yesterday to just see how other people have made a video, and I found an Hindi language video where somebody explained it very nicely. What it actually showed was, it showed twisting of his hand. Twisting of the hand, you can imagine my hand getting twisted here. This part of the hand is not moving, but this part of the hand is moving. Okay, it's getting twisted. In the same way, when I try to do this fiber, which was like this, now it starts getting twisted. So imagine this fiber here, B dash, it starts getting twisted like this. So B dash moves to this, or you can say, suppose if you can call this as B, if you call this as B dash, B moves to B dash. So this is O. So this angle made at this center, now this angle made at the center can be called as theta. Okay, and the amount of torque that you applied is T. So in the case of bending moment, that's in the case of bending moment equation, you applied moment, so it started bending. In this case, you started applying torque. So in place of M, you need to place this torque. Okay, and then this was resisted. Now this is being resisted due to this size of the cross section. Suppose if this cross section is very small, suppose if it is not a rod, if it is like a wire-like thing, you can easily twist it. So definitely if you want to apply more torque, then you need to have this rod slightly bigger. So that means this section really matters. So in the case of beams, what was I? Basically for a rectangular section, BDQ by 12. So I am trying to bend it on one side. Now we know when you keep a rectangle like this, BDQ by 12 form, I think it will be larger. If you keep a rectangular like this, BDQ by 12 will be smaller, because the values of B and D will change. B and D will change here. Here D is larger, here D is smaller. Okay, it will change. So, but for this, now for this circular, it is not bending, it is actually getting twisted. Whether I should take the section like this or like this. So then, what they have done is, they've added the section modulus for circular sections like this. So for a circular section, sorry, it's not still looking like a circle. This is a circle. What is moment of inertia for circular sections I? What is the moment of inertia for circular sections I? Pi d to the power of 4 divided by 64. Okay, so that is for one section. So that is for one section XX, it is pi d to the power of 4 by 64. Again, you look at the Y section. Y section is also circular, no? For that also it is pi d to the power of 4 by 64. So here For bending, it is about one section. For twisting, there is no axis. So you need to add the sum of the resistances in both x-axis and y-axis. So it becomes like I x-axis pi to the power of 4 divided by 64. I y-axis is also pi to the power of 4 divided by 64. So you have something called as J. J stands for polar moment of inertia. Earlier it was called as just moment of inertia. Now this is called as polar moment of inertia because it is about both the axes. Okay, so that polar moment of inertia is the sum of Ixx plus Iyy. Then what is this polar moment of inertia? It becomes 2 pi d to the power of 4 divided by 64, which finally becomes pi d to the power of 4 divided by 32. So J for this, when you add this Ixx plus Iyy, it will become pi d to the power of 4 divided by 32. So you use that Jp here. So for bending moment equations, you use I, which is BdQ by 12. Here you use what? J, which is actually polar moment of inertia. Now in the case of bending, you are looking at whether this stresses at the top are compressive or actually tensile. The top side is compressive and the bottom side is tensile if it is sagging. These are actually normal stresses. These are actually normal stresses acting on the material. But here you can see that a material which was like this, at the surface. Guys, I am saying this. Now if I suppose if I draw a rectangle here, if I twist it, now the rectangle is not a rectangle anymore. Okay, it starts getting distorted. It is shear. Okay, so in the case of bending moment equation, it was normal stress. Okay, in the case of torsion, it is shear stress. And what is the notation for shear stress? So sigma B is P by A. What is actually the notation for shear force divided by shear area? That is tau. So you use tau here. Instead of normal stress, you use tau. That tau is 0 at the center and it actually depends on what radius. If you substitute the radius equal to r, that will give you the tau at that radius. So very similar to the sigma B at any distance y from the neutral axis. If you want shear stress at any radius, you should substitute that r. So here that r comes here. So it is always with that, like, may I sing for you, that is stress for the fiber which is at a distance y from the neutral axis. It is like tau for the fiber which is at a distance r from the center of the rod. Okay, if you substitute this r as 0, that means at the center of the rod there are no shear stresses. It is not actually twisting it off. Okay, so this is this. So you got these 4 terms. Most of the times these 4 terms are sufficient to solve 80% of the numericals. The last 2 terms are with respect to this. So instead of Young's modulus is for normal stress. So stiffness of the material, so that is resistance to normal compression or normal tension is Young's modulus. If it is for shear, we use what is called as G, which is called as the rigidity modulus. So if any body is opposing compression, then we say it is stress by strain formula, we call it as Young's modulus. So Young's modulus gives you how stiff is the material. So that means even with large amount of stress, if there is very small amount of strain, then we say Young's modulus is large. That means the material is stiff. Suppose if you have a material which is held like this, if you apply a force on this side and if the material starts bending like this, I mean, suppose if it is starting to get distorted like this, then you have what is called as gamma here, which is called the shear strain. Instead of Young's modulus, we use a term which is called the rigidity modulus. Rigidity modulus gives you a feel about how rigid is the body. Rigidity is basically its capacity to resist distortion. So distortion means change in shape. Deformation means change in height or change in length. Okay. So if a material is very rigid, so that means even if you apply a force here, it will not get distorted too much. That means this gamma angle will be very small. Okay. So instead of Young's modulus here, you end up having what is called as rigidity modulus G. So G is actually, instead of normal strain, you have shear strain tau divided by, instead of normal stress, you have shear stress. Instead of normal strain, you have got shear strain, which is gamma. So you use, instead of E, you use what is called as G. And here you have to remember this, it is G theta by L. Okay, don't have proper explanation for this. So this is called as the torsion equation. And most of the problems will revolve with this. Usually people don't need to have a lot of capacity to think. They will give you a problem where you need to find out T, and they will ask you to find what is the maximum shear stress. For that, what you have to do, you have to just use this first 4 terms of the equation. You have to first calculate T, or maybe T would be given in the problem itself. Then the diameter would be given for the shaft. So that will give you the radius. If you know the radius or the diameter, then you can find out pi d to the power 4 divided by 32, which is actually Jp. So this is known. If you know the diameter, then radius is known, at which you will have the maximum shear stress. And only thing not known is tau. Okay. So this is the use of this torsion equation. Okay. So can we actually okay, let me stop this.